You know what drives me crazy, Max? When I'm working with an AI system that's great at one specific visual reasoning task but completely falls apart when I ask it to do something slightly different.
Oh, I hear you. It's like having a Swiss Army knife where only one tool works at a time. These multimodal systems are either looking at images and answering questions, or they're generating captions, but rarely can they zoom in on details or mark specific objects in a coherent way.
Exactly. And that's why today's paper is so interesting. It's basically saying, what if we could build an AI that reasons about images the same way humans do, by actually manipulating and generating visual content during the reasoning process?
Welcome to another episode of Totally Unprofessional Peer Review. I'm Max Stone, your resident metrics and methodology enthusiast.
And I'm Casey Park, focusing on structure and flow in AI systems. Today we're diving into a fascinating paper called Omni-R1, towards the Unified Generative Paradigm for Multimodal Reasoning.
This paper introduces a really novel approach to multimodal reasoning. Instead of building separate systems for different visual tasks, the researchers have created a unified framework where the AI can generate intermediate images as part of its reasoning process.
And what's even more mind-blowing is their Omni-R10 variant, which somehow manages to learn these complex multimodal reasoning skills without even needing multimodal training data. It's like teaching someone to paint without ever showing them a picture.
The implications here are huge. If we can get AI systems to reason visually in this unified way, we might finally break out of these task-specific silos that have been limiting multimodal AI for years.
So stick around as we unpack how Omni-R1 is changing the game for multimodal reasoning and whether this generative approach might be the key to more flexible, human-like visual understanding in AI systems.
Let's talk about the evolution of multimodal reasoning in AI. The paper mentions that early approaches to multimodal reasoning were actually quite limited. They focused almost exclusively on pure text-based reasoning.
Right, which is kind of ironic when you think about it. You have these multimodal systems that could see images, but when it came to the actual reasoning process, everything was converted to text. The image was basically just context for text generation.
Exactly. Then we saw progress with systems that incorporated multimodal information into the reasoning steps themselves. But there's still a major limitation, the authors point out. These systems tend to follow a single task-specific reasoning pattern.
And that's the key problem they're addressing. Let me show you this figure from the paper that really illustrates the diversity of multimodal tasks we need AI to handle. Look at this. We have natural scenes where the AI needs to identify what's on a plate, diagrammatic math problems, structured images like charts and graphs, and even vision operational scenes where the AI needs to understand how to manipulate objects.
And what's fascinating is the bottom half of this figure, which shows the diverse reasoning skills needed to handle these tasks. We've got grounding, with zoom-in capabilities, marking objects, drawing auxiliary lines for math problems, creating bounding boxes, and even visual prediction.
Exactly. And current systems are typically specialized for just one of these skills. You might have a great system for zooming in on parts of an image, but it can't mark objects. Or you have one that's amazing at drawing bounding boxes but can't predict visual changes.
The paper actually mentions some of these more recent approaches. For instance, they talk about ICOT, which introduced interleaved modal reasoning, where the model adds multimodal evidence during reasoning, and DeepEyes, which uses tools to get new multimodal observations while reasoning.
And MVOT, which generates image text interleave rationales for spatial reasoning. But the key limitation they all share is that they're designed for specific reasoning patterns that don't generalize well across different multimodal tasks.
Let's look at a concrete example of these different reasoning skills in action. The paper provides some great illustrations. Here we can see different reasoning skills applied to different tasks. In example AAA, we have grounding with zoom in to answer a question about what a person is wearing. In B, we see bounding box grounding to identify what's holding T.
And in examples C and D, we see more complex reasoning, marking specific points on a graph and using visual prediction to describe a sequence of robot actions. Current systems typically excel at just one of these skills but struggle with the others.
The paper also highlights another interesting example of a reasoning skill, zooming in on specific regions of an image. Take a look at this example.
This is such a common human behavior. When we need to examine something in detail, we naturally zoom in. But for AI systems, this has traditionally been challenging because it requires generating a new, transformed version of the original image.
And that's where we start to see the limitations of current approaches. The paper mentions that putting generative multimodal reasoning into practice is challenging for two key reasons.
Right, first, there's the challenge of functional image generation. The images needed for reasoning are often unnatural, like images with marked numbers or highlighted regions. That's tough for most multimodal systems.
And second, there's the issue of costly interleaved modal reasoning annotations. Training these systems requires step-by-step annotations of the reasoning process, which are expensive and rare.
The paper also shows us the diversity of tasks that need to be handled. Let's look at this table showing the evaluation tasks they used. They tested on natural scene perception, structured images like charts, diagrammatic math problems, and vision operational scenes. That's a really broad range of visual reasoning tasks.
And this diversity is exactly why we need a unified approach. The authors argue that all these multimodal reasoning skills can be unified within a generative paradigm, what they call Unified Generative Multimodal Reasoning.
That's the key innovation here. Instead of having separate systems for zooming, marking, drawing bounding boxes, etc., they're proposing a single system that can generate intermediate images during the reasoning process to handle all these tasks.
It's like the difference between having a bunch of specialized tools versus having one really versatile multi-tool. The specialized approach might work well for specific tasks, but it breaks down when you need to handle a diverse range of problems.
Exactly. And this is why the Omni-R1 approach is so interesting. It's trying to break out of these task-specific silos that have been limiting multimodal AI systems.
So now let's get to the heart of this paper, the Unified Generative Multimodal Reasoning approach that Omni-R1 introduces. This is really the key innovation here.
Exactly. The authors propose a completely different paradigm. Instead of having specialized systems for different visual reasoning tasks, they create a single system that can generate intermediate images during the reasoning process.
Let's look at the framework they've developed. This diagram really shows the two-stage approach they've taken with Omni-R1.
This is fascinating. You can see they've developed a two-stage framework. The first stage is what they call PeSFT, perception, aligned supervised fine-tuning. And the second stage is PeRPO, perception, calibrated relative policy optimization.
And notice on the left side, they're starting with limited visual annotated interleaved trajectories. That's a fancy way of saying they have a small dataset where humans have created step-by-step reasoning examples with both text and images.
Right. And what's really clever about their approach is how they handle what they call functional image generation. Remember, these aren't just pretty pictures. These are functional images with specific purposes, like zooming in, marking objects, or drawing bounding boxes.
That's where the perception alignment loss comes in during the first stage. The paper mentions they combine a standard cross-entropy loss with this perception loss to ensure that the generated images are actually useful for reasoning.
And in the second stage, they use reinforcement learning with what they call a perception-calibrated reward. This reward has three components: accuracy, format, and perception.
Let's break those down. Accuracy is pretty straightforward. It measures whether the final answer is correct. Format checks if the model is following instructions correctly. And perception evaluates the quality of those intermediate images the model generates during reasoning.
What I find particularly interesting is that they're combining these rewards using a weighted formula. The paper mentions they use the formula R, Sigi Rai, Sigi Rai, Sigi Rai, Eski Rai, Eski Rai, Sigi Rai, Sigi Rai, Sigi Rai, Sigi Rai, Sigi Rai, Sigi Rai, Sigi, Vigarai, Sigi Rai R, Phi, Sigi Rai R, P, Rai, Rai, Sigi Rai R, Sigi Rai, Sigi Rai, R, Sigi Rai R, P, Sigi Rai.
Let's take another look at some examples of how this unified generative approach works in practice. This figure really shows the power of generating intermediate images during reasoning.
This is such a great visualization. In example AA, we see the model zooming in on a person to answer what they're wearing. In example B, it's drawing a bounding box around a teacup to identify what's holding tea.
And in example CE, it's using bounding boxes again, but for a more complex task, interpreting a parameter in a graph. Then, in example D, it's marking nodes in a graph to determine if it's connected.
The most impressive might be example E, where it's doing visual prediction, showing a sequence of robot actions to move a donut into a drawer. This is really demonstrating how one unified approach can handle all these different reasoning skills.
And the results seem promising. Let's look at the performance table from the paper.
You can see that Omni-R1 variants are significantly outperforming the baseline models across different task categories. The Omni-R1M model, for instance, shows an 87.7% improvement over the baseline on average.
What's particularly interesting is how well it performs on diagrammatic math problems and Zisian operational scenes, which are traditionally very challenging for multimodal systems.
Let's also look at this ablation study they did. It really shows the importance of that perception-calibrated reward we mentioned earlier.
Right. When they remove the perception reward component, performance drops significantly across all task categories. This suggests that guiding the model to generate high-quality intermediate images is crucial for effective reasoning.
One thing that really strikes me about this approach is how it mimics human reasoning. When we're trying to solve a complex visual problem, we often mentally zoom in, highlight parts, or visualize changes. Omni-R1 is essentially doing the same thing, but explicitly generating those visual steps.
That's a great point. And it's not just mimicking human reasoning, it's making that reasoning process transparent and interpretable. When the model generates these intermediate images, we can actually see how it's approaching the problem.
Let's take another look at that zoom-in example from earlier in the paper. It's such a simple capability, but so powerful for reasoning.
This is a perfect example of functional image generation. The model isn't just generating a pretty picture, it's creating a zoomed-in view that serves a specific purpose in the reasoning process. And that's exactly what makes this approach so versatile.
And what's remarkable is that they're doing all this with a relatively small amount of training data. The table we saw earlier showed they only used 100 samples each for natural scene perception, structured image tasks, and diagrammatic math problems, and 300 samples for vision, operational scenes.
That's a great point. Let's take another look at that table to emphasize just how little data they're working with.
Right, just 700 samples total across all these diverse tasks. That's incredibly efficient compared to most deep learning approaches that require massive datasets.
So to summarize this section, Omni-R1 introduces a unified generative approach to multimodal reasoning, where the model generates intermediate images as part of its reasoning process. This allows it to handle diverse reasoning skills like zooming, marking, drawing bounding boxes, and visual prediction, all within a single framework.
And they achieve this through a two-stage framework with perception alignment loss and perception-calibrated rewards, which ensures that the generated images are functional and useful for reasoning. The results show significant improvements over baseline models across a wide range of multimodal tasks.
Next, we should talk about the even more surprising aspect of this paper, Omni-R1, which somehow manages to learn these complex multimodal reasoning skills without any multimodal training data at all.
Now we come to what might be the most surprising part of this paper, Omni-R1. This variant somehow manages to learn complex multimodal reasoning skills without needing any multimodal training data at all.
That's right, and it's pretty mind-blowing when you think about it. The paper describes Omni-R1 as eliminating the need for multimodal annotations by bootstrapping stepwise visualizations from text-only reasoning data.
Let's look at how they actually accomplish this. The diagram from the paper really helps explain the approach. See the right side of this diagram? While Omni-R1 starts with limited visual annotated interleaved trajectories, Omni-R1 starts with something completely different, just text-only chain of thought seeds.
And then it does something really clever. It bootstraps stepwise visualizations from those text-only reasoning examples. Essentially, for each text reasoning step, it generates a corresponding image.
Right. It's taking text step K and creating image step K. This creates what they call synthetic interleaved trajectories, basically artificial examples of multimodal reasoning that weren't created by humans.
What's fascinating is that these synthetic examples aren't meant to be perfect. The paper explicitly mentions that they're not intended to be perfect supervision, but rather to teach the interleaved reasoning format and expose intermediate multimodal states.
It's like learning to paint by first sketching with a pencil. You're not creating masterpieces right away, but you're learning the basic process and structure.
And once they have these synthetic examples, they feed them through the same two-stage process we discussed earlier. First, the perception-aligned supervised fine-tuning, then the perception-calibrated relative policy optimization.
Let's look at an example of what Omni-R1 actually produces. This is really impressive. Here's a simple question. Which of these would appear shinier when polished? A. Metal spoon, or B. Wooden spoon? And you can see how Omni-R1 handles this with generated images at each step of reasoning.
In step 1, it generates an image showing both types of spoons and notes their colors. Then, in step 2, it generates another image highlighting the metal spoon and explains why it would be shinier when polished.
What's remarkable is that this reasoning process with generated images was learned without any human-created examples of image-text interleaved reasoning. It's bootstrapped entirely from text-only reasoning examples.
And the most surprising part? Let's look at the performance results. This table shows how Omni-R1 compares to Omni-R1 and the baseline models.
The results are honestly shocking. Not only does Omni-R1 match Omni-R1's performance, in some cases it actually outperforms it. Look at the Omni-R1's variant. It achieves an average score of 50.19, which is higher than both Omni-R1 variants.
And that's a 105.5% improvement over the baseline. What's particularly interesting is where Omni-R1 excels. If you look at the MMVet column, which tests comprehensive multimodal reasoning, Omni-R1 variants score significantly higher than Omni-R1.
The paper also breaks down performance by task type. Let's take a look at that.
This table shows that both Omni-R1 and Omni-R1 outperform the baselines across all 4 task categories. But what's interesting is that the gains are most pronounced on the vision operational tasks, which are typically the most challenging for multimodal systems.
And notice the bottom row. When they remove the perception reward component, performance drops significantly. This suggests that guiding the model to generate high-quality intermediate images is crucial for effective reasoning, even when starting from text-only data.
The paper also includes this fascinating visualization comparing Omni-R1 and Omni-R1.
This is a TS&E projection of the reasoning traces from both models. You can see that Omni-R1 on the left has more compact, concentrated clusters, while Omni-R1 on the right is more dispersed and multimodal.
The authors interpret this as showing that trace supervision in Omni-R1 promotes canonical and stable generations, while the reward-guided approach in Omni-R1 encourages broader exploration that can still support correct decisions.
In other words, Omni-R1 is finding more diverse ways to solve problems, which might actually be an advantage in some cases.
The paper also notes some interesting differences in where each model excels. Omni-R1 is generally stronger on perception-oriented evaluations, reflecting better fine-grained visual perception. But Omni-R1 is more competitive on reasoning-oriented tasks and performs strongly on comprehensive benchmarks.
It's also worth noting that Omni-R1 performs better on PeRPO, which suggests better evidence consistency and reduced hallucination. That's particularly impressive for a model that wasn't trained on human-created multimodal examples.
So what's the big takeaway here? I think it's that we may not need as much multimodal training data as we thought. If we can bootstrap multimodal capabilities from text-only reasoning data, that could dramatically reduce the cost and effort of training these systems.
Exactly. Creating those step-by-step multimodal reasoning examples with both text and images is incredibly time-consuming and expensive. If we can achieve similar or even better results using just text-only reasoning data, that's a game-changer for multimodal AI development.
And it suggests something deeper about the relationship between language and vision. Perhaps once a model has learned to reason well with language, it can transfer those reasoning skills to visual domains with relatively little additional training.
It's almost like language provides the scaffolding for reasoning, and then the model can learn to hang visual concepts on that scaffolding. This could have huge implications for how we approach multimodal AI training in the future.
To summarize this section, Omni-R1 demonstrates that it's possible to achieve state-of-the-art multimodal reasoning without multimodal training data by bootstrapping stepwise visualizations from text-only reasoning examples.
And surprisingly, this approach not only matches but sometimes exceeds the performance of models trained with human-created multimodal examples. This suggests a promising direction for making multimodal AI development more efficient and accessible.
So there you have it. Omni-R1 is pushing the boundaries of multimodal reasoning by unifying diverse visual skills under one generative framework. And perhaps most surprisingly, Omni-R1 shows we might not need expensive multimodal training data after all.
Absolutely. This could democratize multimodal AI development and bring us closer to systems that reason about images the way humans do, by actually manipulating visual content during the reasoning process. I'm excited to see where this research leads.
For totally unprofessional peer review, I'm Max Stone.
And I'm Casey Park. Join us next time when we'll be exploring another cutting-edge AI paper.
Until then, remember, in the world of multimodal AI, a picture isn't just worth 1,000 words, it's worth at least a dozen intermediate reasoning steps.